Well, hello everyone. Welcome again to another Abaqus tutorial. And in this one, I'm going to show you and discuss how can you model steel bolt using axial connectors, similar to what I'm showing over here. So I'm going to start this tutorial with a little bit of background. So essentially, there are three main types to model a bolt in finite element models. If you go with the extreme case, the one on the left here, in this one, you model the bolt using solid elements, and you represent the bolts with two independent parts, one for the bolt itself and another one for the nut. And as you notice from this kind of model, you are representing the geometry of the bolt, including the threads in all of its details. And these kind of models can be computationally expensive and more demanding in order to actually model the bolt geometry and mesh it and so on. These kind of models are still available in the literature, and they are generally used to investigate the interaction between the nut and the bolt threads, and maybe looking at other situations like how the preload in the bolt is affected by the turn of the nut, or looking at bolt thread stripping in some cases. Now, for most other applications that are looking for the overall behavior of a connection or a joint, you wouldn't need to have this sophisticated bolt model. Instead, you can represent the bolt using one solid part as shown over here. And in that case, you just represent the bolt head and the nut with round solid elements. And for the grip length of the bolt, you represent it with an equivalent cylindrical solid parts. One that would represent the shank or the nominal diameter, and another one that will represent the threaded portion, if this is a partially threaded bolt, for example. So this is the one that most commonly found in the literature for these kind of simulations. In this one, you will need to define the material properties and the stress-strain behavior of the bolt. And if you want to include damage, you need to calibrate the material parameters for the damage to simulate failure in the bolt. Now, if you want to go more simplified way, is to represent the bolt using axial connector, as we are showing here, between two reference points. And this axial connector or axial spring will represent the overall force elongation response of the bolt. Now, of course, going with the axial connector model, which what we are discussing in today's tutorial, reduces significantly the computational time for your analysis, because instead of doing a solid bolt with refined mesh, which is typically the case if you want to simulate fracture, and then if you have multiple bolts in your model, then this makes the computational time exponentially increasing. So representing the bolt as an axial connector is a very good alternative. And as we are going to show today, if you are looking for many types of connections, using the axial connector model would suffice in your simulation and would result in pretty much the same results, like on a global scale, as the equivalent shank model or the detailed threaded solid model. As I mentioned, this axial connector modeling approach has some limitations. This axial connector or axial spring is valid as long as the bolt is subjected to predominant tension, which is actually the case for most kind of steel joints or connections, as the ones, for example, that we are showing over here. So this approach would be valid in that case. In all of the cases shown here, the bolt is not only experiencing pure tension, it's experiencing tension and some shear and bending. But as long as the shear force to the tension force is less than 0.2, as shown in past research, the effect of the additional shear force would be minimal on the bolt's force elongation behavior. In summary, for all of these cases, you can use an axial connector with no problem. If you are dealing with a bolt that's subjected to pure shear or predominant shear, for example, if you have like a shear tab connection, or if I'm looking here at this connection that I'm illustrating over here, if I'm looking at those bolts on the beam flange, those will be subjected to shear. So those you will not be able to model them with the axial connector, and you are perhaps better off with the other solid model. So for all the cases here, we can use the axial bolt connector, and this will save us a lot of computational time. How do we represent the bolt in the model? Well, the components of your model are as follows. So we will be modeling the bolt head and the bolt nut as solid elements. This is not necessary, but it is what we recommend, because including the bolt head and nut mean that you will be capture the stress distribution properly in the connected components and any yield line pattern. Of course, I don't need to have those meshed with a small mesh. I can mesh them with a sufficiently large mesh, no problem. And then you will need a reference point at the middle of the bolt head and at the middle of the bolt nut, as you see here in the inner surfaces. And those reference points will be tied to the bolt surface and to the nut surface, each one of those. And then you are going to connect these reference points together using a wire element. And this wire element will be assigned the force elongation behavior. The distance between the nut and the head represents your grip length or the total thickness of your connected components. You should note here that we are using reference points instead of connecting the wire element directly to the middle point of your solid part, because if you connect the wire elements directly to the nodal points of your solid parts, this will cause stress concentrations and will be incorrect. So this is why you need to connect this to a reference point, and the reference point is connected with a rigid body constraint to a surface. And we have discussed the idea of using reference point in previous tutorials. You can refer to those to understand this concept. Now, let's go to Abaqus and see how we can actually model this axial connector model. All right, so now we are back here in Abaqus, and we can see that I already have this model opened. This is a model that I already have from before. It's a model of a beam to column join with an end plate connection. And we can see here we already have bolts in place, but actually the bolts that I modeled before, these are solid bolts, and we need to change that. So if I go to my part, this is the bolt that I had from before, and now I need to remove this part in the middle. I want to cut it out. So how can I do this? I can do that using the cut extrude option. I need to draw like some kind of sketch and then extrude this so that these parts are all cut out. In order to do that, I need to have a plane to draw my sketch, but I need this plane to be somewhere over here. So I can create a datum plane like that. I'm going to do it like an offset from the middle plane over here. I'm going to select a point rather than entering a value. I'm going to place my new plane at this location, at the edge of the bolt. This should be fine. Any actually location outside of the shank area should be fine. And then I'm going to use the create extrude, cut extrude option. And it's telling me select the plane that you want to draw your sketch. So this is my plane. And then I want to select an edge or an axis that will appear to the right. So I will select this one. And then we are in the sketch module right now, and it's waiting for me to draw a sketch that will be used to cut this part. Just to draw a rectangle to cut these parts, I'm not going to go very specific with the coordinates or with the location of my cut. This is just for demonstration, but I will just do it as accurate as possible. So it's roughly from here. This is the edge of the nut to the edge of the head around, let's say here. That's it. It doesn't matter for my sketch to be the exact shape as my bolt shank. It doesn't matter because we are cutting this out. So as long as you're encompassing the entire shank, that should be fine. Then I'm going to select done. And now I'm choosing how I'm going to do this cut. So it should be in this direction. This is correct. So I leave it as it is. And I'm going to cut throughout the entire part. I'm going to say OK. So that's it. So now I cut this entire part. So now my bolt is as intended. Of course, I'm doing that because I've already drawn the part with the solid shank. But if you are doing this from scratch, then the only thing that you need to do, you just need to draw the head as an extruded solid. Then you can make another construction plane like this one, and then make another extrusion from this plane for the nut. But this is the better way to do it. Instead of creating the head, the bolt head and the bolt nut as separate parts, because if you do that, this will mean more work for you later on when you are moving this to the assembly. You will need to start positioning both the nut and the bolt head separately. But now if I have it in one part, it's exactly the same. They will be behaving separately because they are not connected, but in the same time, you just deal with them as one part. Now, if I go back to my assembly, I can see that my bolt is like as it is, but I cannot see what's really going on. So just for visualization, I'm going to remove some of these areas. I'm going to select here the removal tool. I'm going to remove some of these cells. So I'm going to select cells. I'm going to select these cells, remove them so that we can get a closer look of what's going on with the bolt. And also we need that later on when we're going to assign the connector and so on. We need to have access to the selection within the bolt. So if I remove these parts, I can see here my bolts. I can see the bolt head, the bolt nut, and nothing is connecting them in between. In this model also I have a washer, but this is optional, of course. It depends on what you are trying to model. So there is nothing joining them at this point. What we need is to join them using a wire element. If I go to the interaction module, this is the wire element. But if I go now and click on the wire element and create a wire element between this node and this node, as I mentioned earlier, this will cause stress concentrations because you are just pulling on single node, which is not good. Instead, we need to do a reference point and rigid constraints. From the same module, the interaction module, I'm going to create two reference points. I'm going to create one in the middle of the bolt head, and then I'm going to rotate like that, and then I'm going to create another one in the middle of the nut. So now I have two reference points. I'm done with that. Before I draw my wire element, right now these reference points are just geometrical features. They are not really connected to anything. They are just flying in the model, although they look like they are on the bolt head or on the bolt nut. So we need to connect them first to the corresponding component. So we can do that with the rigid body constraint. So I'm going to create a constraint, rigid body. You should give it a proper name, of course, but for now, for this tutorial, I'm just going to use the default. I need to select the reference point. We have done this in the previous tutorials. And then I'm going to use the pin option. I don't want to create a set. And then I'm going to select the surfaces that this reference point is connected to. So I'm going to select all these surfaces. If you want to be more accurate, you can, of course, partition the bolt and select only the inner part of the bolt rather than the outer part. This is, again, if you want to be a little bit more accurate, but I don't think this will make major difference in your simulation later on. I'm going to create another constraint for the nut. I'm going to create a reference point. Same thing, select the surfaces. So let me rotate my view. And then I'm going to select these areas. Done. That's it. So now I have my reference points, and the reference points are connected physically to the corresponding components. Then I start creating my wire. So I click here on wire feature. So I'm drawing a polyline. Here you have several options to drawing the line, disjoint wires, chained wires, wires to the ground, many options. In our case, because I'm drawing just one segment, so then it doesn't matter which option I use, it's just one element joining 2 points. I don't want to create a set for this wire element. And then I'm going to select the add button. And I just need to select the first point. So I'm going to select my reference point, I'm going to select the reference point number 1. And then I'm going to select reference point number 2. And then I click done. That's it. So I get it over here. And then I'm going to say OK. And I'm done. So now you can see here your wire connector. It has like this blue color dashed line joining to indicate that you have the connector over here. Now, as you might imagine, the only issue with using the wire connector is that you need to do this process of defining the reference point, the constraints, and the wire elements for all bolts in your connector. So I need to do the same for all other 8 bolts. So I just need to repeat that very quickly. Of course, if you are doing that with Python script, then this doesn't take any time because you can do this in an automated manner. But if you are doing it manually, then you need to do the same process 8 times. So now the next step is that we need to assign the behavior to this wire element. So let's go back to our PowerPoint slides and discuss how this is done before we come back to Abaqus and actually assign a section or a behavior to this wire element. So now that we have modeled the bolt and we defined our reference points and we drew our wire element, what we need to do now is to assign a behavior to this wire element. So in order to do that, we need to define a connector section. This connector section is equivalent to a material model when we are dealing with solid elements. But instead of defining stress strain, here we are defining directly the force elongation response of the bolt. How does a bolt response looks like in tension? It looks like what we are showing over here in this slide. So if you have a bolt, you apply a force F, the bolt will elongate as shown over here by delta, and eventually it will fail after necking in the threaded portion. In this force elongation plot, this is how the solid black line shows you the typical nonlinear behavior of the bolt. You can idealize this using a tri-linear response, which is what we are going to do in this tutorial. And similar to a material, we will need to define first the elastic part, the elastic stiffness. Then we are going to define the plastic component. And finally, we are going to define the strength degradation part, or what we call in Abaqus the damage behavior, until the bolt is totally fractured or fails in tension, where in your simulation the wire will be broken. So the question now, how can we get these parameters for this force elongation behavior? We have a tool, it's called the Bolt Connector app, and it's one that results from a recent paper that our group published. You can use this QR code over here to download the app, it's for free. And in this app, you can select your bolt, you can select the thread type of your bolt, the size of your bolt. You will need to specify the bolt length and the grip length, and how many washers are you using and how many nuts are you using, as well as the grade of the bolt. And once you do that, automatically you are going to get here your force deformation relation. And you can see here the parameters, the numerical values of these parameters over here on the right side. So those are the ones that we are going to take and input in Abaqus to model our connector section. This is a reference paper discussing how this model was developed. This is an open access paper, so you can download it from this QR code for free. So now that we have the force elongation response defined, then we just need to put this into Abaqus. The steps to do that is as follows. So the first step would be to select the connector type. And in our case, we will be selecting an axial connector for the bolts, because we're just modeling axial elongation. Then we will be defining the properties of this axial connector or axial spring. This will start with the elastic behavior, followed by the plastic behavior or the hardening behavior. And finally, we will be defining the damage, which is the drop in strength until failure, which is the damage behavior, including the damage initiation and the damage evolution. These steps we are going to discuss in Abaqus directly, how to input this data. So let's go back to Abaqus and see how to do that. Okay, let's do now this procedure of defining connector section. So you can do this over here, create connector section. I'm going to click on that. I'm going to leave the default name over here. There are many types of connector options that you can select from. I'm going to use the basic one, and I'm going to use for the translation, I'm going to use axial translation. I'm going to click on continue. Now I'm inside the definition module, and I need to start defining the behavior, very similar to what I do with any material. So the first thing that I need to define is the elasticity or the elastic branch. So I click on that. I'm going to do the elastic part is a linear part, and this is assigned to the F1 because this is the local longitudinal direction of the connector. And I need to just input here the value of the elastic stiffness. As we have seen from the Bolt Connector app, we have those values. So if I open those values here on the right, the first value that I need is the value of Ke over here. So this is my axial stiffness. So I need to put this value over here. So that's 490 kilonewton millimeter. I'm using Newton and millimeter as my base units. So this will be 490 and then 3 more zeros at the end to make it Newton per millimeter. That's it for my elastic definition. Then I go and define my next part, which is the plastic behavior. Again, I'm going to assign this to the F1 direction. And right now, I need to provide what is the yield force and what is the corresponding plastic motion. If we go back here to our data from the connector app, my yield force is 576 kilonewton. So that will be 576,000 Newton. And my plastic motion, this represents the plastic elongation of the ball from the onset of yield till the ultimate point, which is this value over here, 2.4 millimeter. So I'm going to go here and then I put 2.4 millimeters, same as my units. For the rate, I'm not doing any rate dependency in my model, so I will just keep this empty. If you have some rate dependency, then you can put this value. In the reference paper that I showed in the slides, you can read more about the inclusion of rate dependency for steel bolts. So now I'm done with the plastic behavior. Then if I want to simulate damage and the failure of the bolt, then I need to add a damage behavior. So I click on damage. And then again, I need to select F1. So this is here, I need to define the initiation. So this is where damage will start to occur. So after the ultimate point, when does this happen? So you can define this based on a force, or you can base it on a motion, or based on like absolute elongation, or based on the plastic elongation. So I'm going to use the plastic elongation in my case, just to be consistent with the output that I have from the connector app. And over here, I just need to provide the values that define the onset of damage. So if we go back to the connector app, my onset of damage, it happens at this point over here. So this is where damage starts and then the stress goes down. So it happens at a plastic motion of 2.4. So I'm going to put the value of 2.4 and the rate, it's irrelevant. This only tells Abaqus when does damage initiate, but it doesn't tell it how does damage progress from this point forward. In order to do that, you need to select this other tab, the evolution. And here I'm going to define the evolution, like, or how does the strength degradation goes after the onset of damage. I'm going to use the tabular option here for the evolution softening. And here I need to specify this damage variable and the corresponding plastic motion. So the damage variable is 0 because there is no damage when the plastic motion is 2.4. It's after 2.4 where you start getting damage. So at 0, it's 2.4, the one that we defined earlier. And then we need to define what's going on afterward, this slope over here. I need to specify the value of the Dmax, which is specified by the connector app over here. This is 0.32, and this represents, in my case, this point at the end where total failure happens. So this point is Dmax 0.32, I put 0.32, and I need to specify what's the plastic motion corresponding to that. The corresponding motion corresponding to that will be this plastic elongation from the onset to the failure, which in my case, this will be the 7.5 value over here. Let me use the yellow marker. So this 7.5 minus 2.4, which gives you 5.1. After I reach this point, I want failure to occur. So this means that after this point of Dmax of 0.32, Dmax will be 1, meaning it will be broken. I will put the value of Dmax here equal to 1, and then I need to specify the plastic motion. I can put it the same as the previous one, as 5.1, but in general, when you have like a very sharp drop, this changes the stiffness of your model very quickly, and this might cause some conversions if you are running this with the static solver. So it's better maybe to multiply this value by a little bit like increase it 5% or something like that, just to have like a little more smoother failure. So I can put this like, for example, as 5.15 over here. Then I click OK, and that's it. Now I have my connector defined. The only thing remaining is to assign the connector to the wire. So you can do this from the create connector assignment. It will tell you select the wires that you want to assign this to. I'm going to select that. Click done. And then I need to select my connector. I only have one section defined. So I click OK. And now you can see that it writes Axial. This is the type of the connector. It already says that on the wire. And now you are done. Then the only thing remaining is to run the simulation and observe the results, which I will show you back. We go back to the slides and we show how does this look like after you are done. Back to our slides. Here I'm going to show you the output, like the simulation of this bolt connector approach. And in this one, I'm showing a cross section to show exactly what's going on between the plates. So we can see here the gap between the plates, and we can see the connector here and the 2 points for the wire element. And if I play the simulation, you can see here your beam and your column are being deformed, and you can see the components of the end plate is deforming. And eventually, after you reach the failure elongation, then the bolts start failing. How does this compare to a solid bolt model? So as I mentioned in the beginning of my presentation, it is exactly the same in terms of global behavior. If you do the simulation with an entire solid bolt with very refined mesh, you will get pretty much the same response as the one with the wire connector. You can also see if you extract the force deformation of your joint or your connection, and then you plot this, you can see that basically there is no significant difference between the two simulations, and the prediction of the failure behavior of the bolt, whether it's connector, whether it's solid, it's the same. So in that case, a connector bolt would be much more efficient to include in these kind of simulations.
One final important consideration to take into account when using the axial connector modeling approach. As I noted in the beginning of the tutorial, this approach is valid for many types of connections whenever you have the bolt under tension or under tension and small shear. This is the case for all of these examples that we see here in this slide. In all of those cases, the axial connector is acceptable because the bolt is being elongated in tension until failure. So this is what we see over here. The two reference points are being pulled apart in all of these examples. You have just to note that there are some cases where the axial connector option would not be appropriate or will not yield accurate results, specifically when it comes to ductility. This includes cases where the bolt is in pure or dominant shear, as I mentioned earlier in the tutorial. But there are also special cases in tension that you should treat carefully. This is one of those cases. So in this case, the bolt over here, the bottom bolt, is fine because this bolt is subjected to tension. And you can see here that the two opposing reference points or the bolt holes are aligned during the loading. But in the top one, we have an issue. The issue is that the connected plate is bending or deforming in a way that pulls the plate downwards in shear, while the bolt head is rotating, but not moving sideways or elongating the bolt. So it's just rotating. This is comparable to what we call mode 1 deformation that is described in Eurocode 3. In reality, this downward movement will be restricted by the bolt shank, but this doesn't happen, of course, in this case because the wire connector doesn't have any physical representation. So this plate is allowed to keep moving downward with no restriction. In this case, therefore, it would be recommended to use the solid modeling approach for this specific bolt instead of the axial connector. Or you can still use the connector bolt model, but you will need to add an additional constraint to limit this relative shear or slippage movement between the plates. For your typical plus minus 1 millimeter bolt hole tolerance, a 2 millimeter limit should be imposed for this relative vertical or shear motion, which this is something that you can do by defining an additional wire connector that will be acting in shear between the two bolt hole surfaces. So I hope that these considerations or limitations for the axial connector approach are clear. Still, there are many applications similar to the ones that we demonstrated for this approach that will still save you lots of computational time. Thank you again for watching this tutorial, and I hope that you found it useful, and I'll see you in the next tutorial.